Ecophysiology of host pathogen interactions. Climate warming causes varying host pathogen responses. For example, R. ondatridae, a parasite that infects amphibians, has an increasing infectivity rate with increasing temperatures. The amphibians' defenses also increase with temperature, leaving maximal pathology to occur at intermediate temperatures. Whereas another study shows the virulence of both a coral fungus and a protozoan increased with temperature. Such differential responses can complicate attempts to predict net effects. Metabolic theory of ecology is a way to predict host pathogen responses to climate change by using established relations between metabolism, ambient temperature, and body size. It is a promising approach for the prediction of disease that avoids using detailed species-specific development and survival parameters. This approach facilitates general predictions on how infection occurs with patterns in changing with warming. A study that tested this is the strongylid nematode study, where metabolic theory of ecology was used, and traditional host parasite transmission models were also used to examine how seasonal temperature changes and annual temperatures affect the strongylid nematode's reproduction. By casting reproduction in terms of temperature-induced trade-offs between parasite development and mortality, this approach facilitated both general predictions about how infection patterns change with warming. Community ecology, biodiversity, and climate change are all contributing factors of host pathogen interactions. Host pathogen interactions are embedded in diverse communities, with climate change likely leading to loss of some of these interactions. An example is the wider Caribbean region. This region is considered a disease hotspot characterized by rapid warming-induced emergence of multiple new pathogens that have caused precipitous coral declines within the ecosystem, causing ecosystem-wide repercussions. Ecosystem-wide repercussions are often seen when a keystone species is affected. If a host is a dominant or keystone species, the effects of disease may cause rapid decline in the population, which in turn can cause widespread community shifts across trophic levels. For example, near extinction of the once dominant herbivorous abalone by warming-driven rotosicle disease caused pervasive community shifts across multiple trophic levels.
Community ecology, biodiversity, and climate change. Commensal microbes will act on a host immune system when a pathogen is detected to prevent invasion or colonization via protective responses. Mutualistic microbes are microbes that benefit from the host and the host benefits from them. According to the article, an increase in global temperatures could cause microbial communities to shift from mutualistic to pathogenic. An increase in global temperatures could also suppress mutualistic microbes' ability to produce antibiotics in plants. Biodiversity loss could lead to pathogenic growth and higher rates of pathogen transmission. Shifts in behavior, movement, and phenology of host and parasites. Phenology is defined as the study of seasonal phenomena focusing on the relationship between climate and plant and animal life. Migratory species migrate to multiple environments to best meet their needs, usually focusing on climate needs in their migration. The increase in global temperature has already caused an increase in parasite transmission during times of the year where parasite transmission is lowered. The increase in global temperatures can affect parasitic development stages in many ways, as the developmental stages all show different sensitivity to temperature.